this is the end of 2-4. This is the last of our 4-part thing, and we're not really going to have any notes per se. I'm kind of not going to do the theory bit on this one. We're going to end with just a couple of kind of different types of examples. Different types of examples that you might see in homeworks, quizzes, tests, all those kind of things. So let's jump right in. Oops, wrong button. I need this button. There we go. All right, so you might see this type of problem. This type of problem is a backwards version of what we've seen already. So this problem, we're supposed to write a polynomial function of least degree with real coefficients in standard form, descending order, so what's that saying, that has all of these factors in it. So this time we're given all the zeros and we've got to write the function. And so basically, these type of problems are really straightforward, which is why I teach this the way I teach it in here. There's no real reason for now to kind of get the theorems written out formally for this. It's easier to just kind of show you what to do. So this is going to be f of x equals, now for these real zeros, you do it like you'd expect, right? So it's going to be x plus 3, right? The sign's going to flip because it's a 0, same as what we've been doing. Now this next one is a 1 with a multiplicity of 2, so that would be x minus 1, flip that sign, multiplicity of 2, so squared, right? Now the other trick with this is when you have complex zeros. So for complex zeros, it's a little bit sneaky tricky, right? So what happens is, because remember in the last lesson I was kind of making a big deal about that complex numbers come in pairs, because they come in the positive one and the minus one. So we have to use the conjugate, really, is what we're doing. And so this one would turn into x plus 4i times x minus 4i. So when we have complex number, I keep doing that, times 4i. When we have complex numbers, that always represents two different factors, right? And it's going to be the conjugates of the two things. And then to finish it out, we just got to do all the distributive property, right? This one, we've got our shortcut happening. So I'm going to start with that, and I'm going to also do this on this line. So this first one we're not going to touch because we've got to deal with all this other mess first. So this first one is just going to stay x plus 3. Now we've got the binomial squared shortcut here. And so this is going to be a squared, so x squared, plus 2 times a times b. So plus 2 times negative 1 is negative 2 times x. This times 2. Negative 1 times x times 2 is negative 2x. And then plus b squared, so plus 1 squared is still 1, right? And then this last one, we'll go ahead and distribute it. Now, since it's a conjugate, what's going to happen here? That outside and the inside are going to cancel, leaving us with just the first and the last. We know that. We've multiplied conjugates in other contexts many, many times. So we don't really have to do all of these. We only have to do this one and this one. We don't have to do the inside and the outside because those are going to cancel. Right, it's going to be 4ix minus 4ix, disappear, right? So x times x is x squared. And then 4i times negative 4i is going to be negative. I'm going to write this. I'm going to go ahead and leave this kind of intermediate bit in here, because that's going to be negative 4 times 4 is 16, so negative 16 I squared. Now, hopefully you remember that I squared actually equals negative 1. So this would actually simplify on down to plus 16. We'll do that in a minute, right? Because we've got other things we can do on this line. We may as well kind of break that up. All right, this we've got to do just big old distributive property looking thing over here, right? We've got x times x times negative 2x, x times 1, and then 3 times x, 3 times negative 2, and 3 times 1, right? We've got to just distribute all out. So x times x squared is x cubed. X times negative 2x is negative 2x squared, right? X times x is x squared. X times 1, that's easy. That's just x. So plus x. And then this next set is 3 times x squared is 3 times x squared. These ones are going to be pretty easy, right? So plus 3x squared, and then 3 times negative 2x is negative 6x. 3 times 1 is just a 3, plus 3. And this is all still times this, but I'm going to go ahead and simplify that out because I squared equals negative 1. So this simplifies out to x squared plus 16, right? Now I've got this big old distributive property. I'm going to go ahead and change colors here. This times this, here, there, and everywhere. In fact, I think I'm going to just do it on this one so as to keep it a little bit neater. I'm going to do it the other way. I'm going to go from left to right because I'm used to doing it that way, right? So x cubed times, excuse me, x cubed times x squared is x to the fifth. It's looking like we've got a fifth degree polynomial, which we could have known because there's 1, 2, 3, 4, 5 factors, right? So then we've got x cubed times 16, which is plus 16x cubed. Moving on to the next one, negative x squared times x squared is minus 2x to the fourth because 2 plus 2 is 4. Excuse me. Negative 2x squared times 16 is negative 32x squared. Next one, we've got x times x squared, which is x cubed, plus x cubed. X times 16 is 16x. Next one, we've got 3x squared times x squared, so we've got plus 3x to the fourth. All kinds of like terms in here. We'll deal with that in a minute, right? And then 3x squared times 16 would be 48. It's getting late. I'm going to just double check for sanity. Go back home. 3 times 16. Yeah, it's great. 48. So plus 48x squared. I'm running out of space. Hopefully we can squeeze it in here. We can't. Clearly we can't. I'm going to have to kind of scoop. I'm going to wrap around and go to the next line. So negative 6x times x squared is minus 6x cubed because 1 plus 2 is 3. And then negative 6 times 16 is going to be 60 plus 36. So 96 is what my brain is telling me. Let's double check. 6 times 16 equals 96. We were right. So negative 96x. Never be afraid to sanity check, y'all. 3 times x squared is 3 times x squared. So plus 3x squared. And then lastly, 3 times 16, we already know this 48. So plus 48. Is that on our screen? No. There we go. That's good enough, right? Okay, so we've got a bunch of like terms. Let's find them. X to the fifth doesn't have any friends. X cubed does. Let's find all the x cubed. I like to, you can do the whole stacking method where you line up the things and do it that way. I like the numbered underline method, as you probably know by now, but that's what I'm doing here. It's helping me keep in line with what's happening. So the x squared terms are going to get 3 underlines. And it gets a little complicated when we've got so many types of terms. Great. And I think that's all our like terms. So all my single underlines are my x cubes. And you're like, why are you doing that? Why not just do it? Well, this helps me make sure I don't miss something and make a mistake. So f of x equals x to the fifth, and then 16x cubed plus x cubed is, oh, look, see, I was going to miss that one because it was on this next line, but that single underline helped me catch it. So 17 minus 6 is 11. So we've got plus 11 x cubed, except I really shouldn't do it in that order. I really should do the next one next. Should do the fourth terms next. That way I don't have to rearrange and write one more line. Let's do these double underlines next. Probably should have done my underlines that way. So negative 2 plus 3 is 1. So plus 1x to the 4th. So far, we're matching what we expect. Now I'm going to do the single other line. So 16 plus 1 minus 6 is 11 still. Beautiful. 11x cubed. And then our x squared terms, which is our triple underline thing. So this one and that one. 48 minus 32 is 16. There any more? 16 plus 3 is 19. So plus 19. X squared. We still matching. We're still doing well. Our next one, we've got the x terms. So 16 minus 96 is going to be a negative something. Negative 80 is what it looks like to me. Negative 80x. Still matching. Look at us. And then that 48 is going to come over by his lonesome. So there is that. It's not really that difficult of a problem, I would argue. It's just a bit tedious, especially with a 5th degree polynomial, right? Let's do one more type of example. This is really the same type of examples we've been seeing before. We're just getting some more specific. So we're going to write this as a product of linear and irreducible quadratic factors and the product of linear factors, then list all its zeros. So what in the world does that mean? Well, basically, we're going to factor this thing, right? So we want to know what are the possible factors. So let's go ahead and graph the thing. Let me pull it up my graph real quick and see if we can find that range, the upper and lower bounds on there. All right, so I graphed the thing, and when we pull it up, so all I did to get this picture right here is I auto-scaled, and then on this calculator, I had to zoom down, or not zoom, but I had to kind of scroll down a little bit, so change my Y values to where it's lower if you don't have touchscreen type of graphic calculator like this or whatever else. But that got me here. Now, I can't see any detail. I don't know where it's going up and down. The auto zoom is just kind of like squashed it all at the bottom and kind of focuses on the end behavior and whatever else. But importantly, and I'm going to double check that I'm not lying to myself. If I look at my x, see this goes from negative 20 to positive 20, and they're counting by ones. So that's why the tick marks on this are so tight, because it's stretched way out, right? This one, but these, I can see all the ones. So negative 1, 2, 3, 4, 5, 6, 7. So it looks like it's between negative 7 and maybe positive 7. Let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Yeah, negative 7 to positive 7. So they're not really getting any bigger than that. So when we go to look at the possible ones, we don't need to stretch it bigger than negative 7 to positive 7. And we could double check with our test and confirm that. But for the sake of time, we're not really asked to do that. And so we're just gonna use the calculator to get what they are. And we're not gonna worry about proving it. We're just gonna assume that those are our upper and lower bounds that are worth sticking to. So possible zeros, right? Our P is 120. That's got a boatload of factors, right? Our P is 120. So plus or minus 120. And the Q is plus or minus 1. That's helpful, right? So we're not asked to list all the possible zeros, so I'm not going to worry about listing all of the possible zeros. That's not really necessary, but this kind of gives us some things that are going to be possible. If we start to kind of get to the lower roots of 120, the lower factors of 120, we're talking about things like 1, 2 definitely is, because it's excuse me, because it's even. 120 is divisible by 3, so 3 would work. So plus or minus 1, plus or minus 2, plus or minus 3, 4, 5, 6, right? A bunch of stuff is possible, right? And so let's start trying some stuff and see what happens. So let's just the sooner we can grab one, the better, because once we have a factor, we can reduce our coefficients and all that stuff. So let's do 1 and see what happens. So let's write down our coefficients. 1, 1, negative 26, 4, negative 120. And to get up to that number, I think we're going to need something kind of large. We may want to jump all the way up to 6 first, but we already started this, so we may as well finish it. It's going to be a hard sell to make for this to work, right? 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. Negative 26, negative 24. There's like no way we're going to get to 120. Let's jump all the way up to a 6, right? Actually, you know what we might want to do is to see the number of possible positive ones, number of possible negative ones. Let's do that real quick so we can get what we can expect. So for the positive real numbers, possibilities, what are our options here? Well, let's see. There's 1 change, 2 changes, 3 changes. So there's 3 changes. Oh, that's nice to know, right? 1 from positive to negative, negative to positive is 2, and then positive negative is 3. So there's 3. There could be either 3 or there could be 1, right? That's nice. Since there's an odd number of possible ones, we know that it definitely has a positive real 0. Definitely has one, right? What about negative real zeros? Let's do that real quick because that might make our lives kind of useful. So I'm going to use this darker blue here and find f of negative x. Now remember from our last chunk that all you really have to do is switch the signs of the ones with odd exponents. So this x to the 4th is going to stay the same, and then this x cubed is going to switch. The x squared one is going to stay the same, x squared, and this x to the 1st is going to change. So minus 4x and then minus 120. Okay, see, this was fairly useful, right? Because if you see here, there's only 1 change, which means there's definitely 1 positive and definitely 1 negative, right? So if we look at kind of our little chart, the positive, negative, and imaginary options here, if we have 3 positive ones and 1 negative one, how many are there total? There's 4 total, right? So there wouldn't be any imaginary ones. If there's 1 positive and 1 negative, then there would be 2 imaginary, right? So that's what we're expecting. We know not one of them's not 1. Now let's go back over here. Let's jump back to where we were. Let's try 6. Why not? You may have looked at the table and cheated, which is totally fine. Totally acceptable. You can figure out what they are and then just prove that they are with this. So 1 and then 1, negative 26, 4, negative 120. Make sure if you do this and double check your amounts and stuff, you don't accidentally put these coefficients because that's gonna mess up your whole problem. Make sure you put the original ones. So bring down the 1. 6 times 1 is 6. I almost said 1. I don't know. 1 plus 6 is 7. 7 times 6, almost said 35. 7 times 5 is 35 plus 42. I don't know, bro. I think it's 26. I don't know. I'm going to double check. I feel like double checking. 42 minus 26. Is that also 26? 42 minus 26 is, see, glad I double checked. It's obviously 16. Positive 16 because the 42 is bigger. 6 times 16 is a big old fat number, somewhere between 48 and 96. It'll be 60 plus 72, I think. What? Let's see. 16 times 6 equals hello. Oh, times 6. Hello. Thank you, machine. Enter. 16 times 6 is 96. I thought we did 9 earlier. 6 times 1, 60 plus, 30. Yeah, obviously, 96. So that's 90. No, how about 100? Ooh, that's not going to work. 600. That's just not going to work. So that didn't work. Now, we know that there's a negative one, so to try to get to that 120, let's try a negative 6 maybe. Let's see what happens here. You see, I know the answers, right? I've got it right over here to my right, right? But I'm modeling here how you would go about figuring it out. You know, just kind of looking at what's there and thinking through how to get to what you're getting to. Negative 120. Now, all this tells us is that we have real positive ones, real negative ones. So they could be ugly, right? So they might be ugly. Now, they're probably not going to be, but, you know, they could be ugly. And by ugly, I mean like awful irrational numbers. That's still a real zero, right? Negative 6 times 1 is negative 6. 1 plus negative 6 is negative 5. Negative 6 times negative 5 is positive 30. Negative 26, that is positive 4. And the 30 is bigger, right? Negative 6 times 4 is negative 24. Negative 24 plus 4 is negative 20. Look at that. We found a winner chicken dinner because negative 6 times negative 20 is 120, and that cancels, giving us a 0. So we found one of the zeros, right? So if we start kind of building our function up here, f of x equals x plus 6 times this guy, right? These are one guy, right? So that would be x cubed, one less than the one we were dividing by, right? So x cubed minus 5x squared plus 4x minus 20, right? So we've got a little bit closer, right? Just a wee little bit closer. So we've got some more factors in here. We're not down to a product of linear and quadratic. That's not quadratic yet. All right, so we got to get up to 20. Well, what do we notice about 20? So what all are our options now? So the factors of 20 are 1 and 2 and not 3 anymore. 3 doesn't go into 20, so we don't need to waste our time trying 3. What else? What else goes into 24 does? 5 does. 6 we've already tried both of. We know what's going on there, right? It could be negative 6 again because we could have like a multiplicity 2 or something like that, right? That's possible, right? So now we also know based on our chart that there's either 3 positive ones with 1 negative 1, or there's 1 negative 1 and 1 positive 1. So we know that there aren't any more negative ones, right? So we know what we want to try is positive. So let's try 5. Why not? Okay, so let's do 5 to see if we can find another one. Now remember that we can use once we've found one, we can use the new coefficients of this new factorable thing, right? So we can do it with 1 and negative 5, 4, negative 20. Right, easy peasy. Bring down the 1. 5 times 1 is 5. Ooh, that's nice. We like that because negative 5 plus 5 is 0. 5 times 0 is 0. 4 plus 0 is 4. 5 times 4 is 20. Now, did I cheat a little bit? Yeah, maybe so, but I don't know. 20 and 5 seemed like it made sense in my head. Also, this negative 5, so I don't know. It kind of, you could have tried 4 first if you wanted. You would have seen there whatever else, but you might have got lucky like I got lucky and found another one. So now we can turn this, use a pale green to see where we came from, right? Turn this into f of x. In fact, I'm not going to put it there, I think, because I'm afraid I'm not going to be able to fit it. We've got f of x equals x plus 6 times x minus 5, right? Remember, we flipped the sign of our 0. And this one less than this one that we were dividing into, so that will be x squared, right? And then plus 0x, right? So just plus 4. Now, so what we have here is kind of that part A, right? This now is the product of linear, so x to the first, and irreducible quadratic factors. This is a quadratic, right? It's the x squared term. So this is now finished with part A, right? That's easy, easy peasy. Let's do the other parts. Move this. Actually, I think oops, hello. Let's move it out over here. I think that's going to be a better place for it, right? So this last part we need to do, so it says and also do it as just a product of linear factors. So how can we do that with this quadratic one? Well, let's solve this one. Let's simplify this one out. So what would this one equal? Now, this one, watch what's going to happen here. We've got x squared plus 4 equals 0, right? If we're solving this out, to get the two other zeros, we subtract 4 from both sides. We end up with x squared equals -4, and then we square root both sides of this, and we end up with x equals, and don't forget, when we square root both sides, we end up with plus or minus. Plus or minus, square root of 4 is 2, and square root of -1 is I. So plus or minus 2i. So to write this as the product of linear only, that would be f of x equals x plus 6. That one was already linear, so was the next one. X minus 5. And then times, and then x plus 2i. And x minus 2i. Right? Easy peasy. And then the last part, that part C, is even easier and peasier. We're going to list the zeros. So the zeros are x equals -6, 5, and plus or minus 2. I don't know why I'm looking over there when it's right there. Plus or minus 2i. So there are all of the parts. And we expected 4 zeros because it's a degree 4 polynomial. And we have 1, 2, 3, 4 zeros. That is it. Wow, this one turned out to be a little bit chunky. But that's all right. There's a lot here. You got this. No big deal. See you later. Bye-bye.